workshop on open domain retrieval under multimodal setting in CVPR 2022. My name is Man Luo, and this is the opening remark. First of all, I would like to thank the organizing team, and without your great effort, it's impossible to run the workshop so well so far. And I would like to give special thanks to our co-chair, Tejas Gokhale, who is also the website chair, maintaining the website and update the information on time. And I would like to thank all the speakers who will share their related work with us and their insights with us. And very excited to looking forward to their talk. And I would also like to thank all the reviewers. So now let's get to the main contents. The topic multimodal is one topic in this workshop, and multimodal connects vision and language, where image is part of the vision and it contains many visual entities that humans interact with. For example, the objects, people, actions, behavior, and also the background. While language describes the visual entities, assigning meaning to what we humans see. And multimodal learning aims to build a shared representation of what we see, that's the vision part, and what we describe it, that's the language part. And with that goal in mind, recently many multimodal tasks and the related data sets has been proposed. For example, in visual captioning, we want the multimodal system to generate the description of image, or we can do the opposite, that we give the image and we give the text and ask it to generate the image. And also we can ask the system to answer the question about image. And recently many multimodal are pre-trained on self-supervised learning task. And one commonality of previous talk is that a system just need to can purely rely on the input contents to predict the whatever human want. And while in many cases, the input doesn't provide enough information and require more information. And here is the retrieval comes to the stage, which aim to search explicit knowledge. And related task has been proposed in vision and language domain, including knowledge-based vision question answering and also open domain question answering. And in many previous multimodal retrieval tasks, it's actually cross-modal. It means that the question and the content, the question and the knowledge are from different sources. For example, the query is the text and the target is the image. Or the opposite way, the target is the image and we want to retrieve the text. We can also do text to image retrieval. So here is a very simple demo given using the CLIP model, which is recently published by OpenAI. So in this example, you can see that user typing sunlight cross pics, and you will see that the clip can find a similar image that match with the description. And we see that the need and the usage of multimodal information retrieval has been increased recently a lot. And for example, Google can allow a user to upload an image, for example, the dance captioning of an horse, and it can return a similar image or related text. For example, here it will find the Wikipedia page about this image. And more interestingly, we can also have multimodal query information retrieval. Different from previous multimodal retrieval, the query in here itself are multimodal, which means that it contains both image and the text. For example, on the left, you will see that the image is about a black dress, while the text says that a blueprint with short sleeve. So the target is a dress that with blueprint and short sleeve. So the system needs to combine both information to get to the target. Similar on the left, you will see that, on the right, you will see that the image is about teddy bear and the question about American president. So the image and the text present different information, and the system needs to integrate both information to find the right answer. And we are very happy to see that recently there is a application about this multimodal query search launched by Google. And the purpose of this workshop is to bring together researchers from information retrieval, natural language processing, and also computer vision to share thoughts and insights in this topic. And we are very delighted to see that many submissions for this topic, and there will be 13 papers presenting in the poster session, and there will be 4 papers presented as spot talk in the end of the workshop. So this is the schedule of the workshop. Now we are in the opening remark, and then we will have 2 invited talks followed by a coffee break. We will come back at 10:30. We will have 3 more talks and 4 spotlight talks in the end. Now let's get to the invited talk. So our first speaker is Dr. Danqi Chen, who is an assistant professor at Princeton University. She received her PhD from Stanford University. Dr. Chen has made significant contribution to the field of open domain question answering and automated retrieval. She has received many awards, including Best Doctoral Thesis Award at Stanford and Best Paper Award at ACL and ENLP. We are very excited to have Dr. Chen as the invited speaker. And now let's welcome Dr. Chen.
Okay, can you hear me? Great, yeah. Okay, yeah, thanks for the introduction, and sorry about this issue. And yeah, thanks. Also, thank the organizers for hosting this workshop. Today, I'm very excited to be here. So before I get started, I actually want to clarify that I'm an NLP researcher. I don't really work on computer vision or multi-modality research. So this talk will be only about text retrieval. So my plan for this talk is to actually outline a series of work that we have done in the past 2 or 3 years. So I assume a lot of audience here don't come from an NLP background. So actually, I don't plan to talk about things too much in detail. So today, I will mainly focus on what are some key ingredients to make these retrieval systems work. And if you don't have a background from NLP, I also hope that this talk can tell you about what kind of retrieval problems we are trying to solve in NLP and why we care about these problems. I also want to mention that I personally have never been to CVPR myself. But we have been learning a lot from the computer vision papers in the past few years. So I also hope to take this as an opportunity to communicate with computer vision researchers. And I hope that we can talk more in the future. So I have been working on retrieval problems for more than 5 years now. So the reason that actually got me really into retrieval was actually because of question answering research. So back to 2016, a lot of researchers were trying to solve this reading comprehension problem, or you probably know this is called the Stanford question answering data set. So basically, given a question like which NFL team represented the AFC at Super Bowl 50, and people were trying to build a system to answer questions based on a short passage of text, and then finally return the answer, which is Denver Broncos. And then in 2017, So we got this actually really interested in this like a more challenging and a more realistic problem. And at that time, we call this problem as open domain question answering. So basically, instead of answering questions based on only a short passage of text, we try to answer questions based on the entire English Wikipedia. So the problem is actually much more challenging because of its scale. So Wikipedia consists of at that time consists of 5 million documents or 20 million passages, or if you count the number of words, it consists of 3 billion tokens. So the problem is actually much more challenging compared to reading comprehension. So at that time, we actually proposed this two-stage retrieval reader framework. So basically, given the question, like which NFL team represented the AFC at Super Bowl 50, we first built a retrieval to find a set of relevant documents. For example, the Wikipedia article Super Bowl 50, and then we use a retrieval reader model. We use a neural reader model to read the retrieved documents and to finally find the answer. So the reader model is implemented as a neural network. But the retrieval model we built in 2017 was actually a standard information retrieval solution based on TF-IDF retrieval. So we call these solutions as sparse retrieval methods. So essentially, we build weighted backwards sparse vectors. And then we build the index for the documents. And then these documents can be searched efficiently with using an inverted index. So this retrieval model component is actually a fixed module and not really trained at all, but it can actually use to effectively narrow down the search space based on the keyword matching. And then in 2019 and 2020, we worked on this project called dense passage retrieval, or DPR in short. So to be honest, I don't really know whether computer vision researchers actually know about this work, but DPR has been getting really popular in the NLP in the past 2 years. So the key idea of DPR is that instead of using a fixed sparse retrieval module, we actually try to train the retrieval using the supervision from a supervised question answering data sets. And the idea of we propose DPR, the key motivation is actually try to address the key limitation of the sparse retrieval, such as TF-IDF or BM25. And we try to build a dense model to actually provide physical latent semantic matching beyond the simple keyword or word overlap or keyword matching. And so you label this kind of semantic matching. So here is one example. So if the question is who is the bad guy in the Lord of the Rings, and the text has a keyword villain, Sauron, and so on. So the sparse retrieval systems will easily fail on these examples, but the dense retrievals actually have the promise to capture these kind of synonyms and paraphrases. And at testing time for the DPR, so during the inference, essentially we need to encode all the text passages using low-dimensional vectors. And then the retrieval can be basically performed using nearest neighbor search, using some tools such as FICE that was proposed in 2017. So I also want to mention that the DPR was actually the development of DPR actually was largely inspired by a work called ODRUM that was actually proposed 1 year ago, in 2019, by a lot of Google researchers. And there's also a concurrent work, it's another really famous work called ODRUM, the Retrieval Augmented Language Model, proposed in 2020, also from Google. So the key difference between the DPR and also the ODRUM and ODRUM is that DPR does not require any extra pre-training. So for the training of the DPR is actually much more computational, is actually computationally much more cheaper. So how is the DPR actually trained? So I don't want to talk about the detail, how these things work in detail. I would like to just give you some high-level ideas. So DPR essentially is just trained using a contrastive learning framework with a supervised question answering data set. And for the positive pairs in the contrast learning, essentially we just use a question and the passage annotated pairs from the question answering data set. And for the negative pairs in DPR, we actually use both the in-batch negatives, basis other passages that come from the same training batch. And also we use a BM25 hard negatives, which essentially we use a BM25 to mine some like similar passages that do not contain the answer to the question. So here's just a simple illustration of the DPR. Essentially, we start with two BERT encoders, one encoder for the question and one encoder for the passage. And we just fine-tune the two BERT encoders using the contrast learning framework with the positive pairs and negative pairs that I just described. And the DPR actually works really well in practice. And I also want to mention, actually, this is just a really fun fact, because DPR has been already more than 2 years at this point. Actually, a fun fact about DPR is that 2 years ago, when we wrote this paper, we actually have never used the word contrast learning in the paper. But at the same time, in the computer vision community, there was this paper, SimClear, that came out also about like 2 years ago. We were actually not really aware of the work like SimClear or MoCo that came out in 2020, but we actually came out something really similar using the contrast learning to learn the retrieval. But we actually didn't even use the contrast learning in the paper, but it's really just an idea of the contrast learning. But still, compared to the SimClear, there are actually a lot of differences in the work of our DPR work, including in the DPR, we actually use dual encoders, like one encoder for the question and one encoder for the passage. But the SimClear actually is just one single encoder for the images. And for SimClear, essentially they use like the data annotations of the unlabeled images. But here we actually use the supervised data. And here the goal of the DPR is actually to do the retrieval, while the SimClear actually tries to learn the pre-trained reputations. And as I said, like DPR actually is a very, very simple idea, but it actually works really well in practice. So 2 years ago in this paper, we showed that so DPR actually can significantly outperform the BM25 by a very large margin. So from this slide on the left, you can see it's actually the result of the retrieval performance. So the blue curve here is the BM25 result. And the orange curve means that we train the DPR using only 1,000 examples. And all the other curves basically correspond to training the DPR using a different number of training examples. So basically we show that using only 1,000 examples, DPR can already outperform BM25. And on the right side of this slide, we also show that basically like using DPR instead of the BM25, the better retrieval performance can also translate to better end-to-end question answering performance. Okay, so this is basically what I want to tell you about the DPR. Again, the work has been actually really popular in NLP and has been already still for 2 years. So after 2 years, what we have learned from this work, DPR. So I actually deeply believe that the success of DPR actually largely depends on the pre-trained encoders, such as the BERT. So this is also a very big difference compared to computer vision research. So here, if we have to start with the pre-trained BERT encoders, if we start with the randomly initialized encoders, basically this retrieval model will not work. And we also find that incorporating BM25 negatives would be very crucial for the retrieval performance, and as we actually demonstrated in the paper. And I also want to mention that, so DPR is actually much more computationally cheaper compared to the precursors such as ODRUM or ODRUM. But still, DPR actually requires a pretty large batch size, such as 128, which is actually required to run on 8 GPUs. So 8 32 gigabyte GPUs would be still pretty expensive for at least for the academic labs. So this actually, I would say, the limitation of the DPR work. So after DPR came out, there are actually a lot of improvements actually trying to improve the DPR, including a lot of people propose like using better negatives, such as model-based negatives, or try to use the denoise hard negatives. And there are also some techniques, for example, this I really like this paper called gradient cache, that actually try to have some techniques that actually can resolve this like the large batch size issue. So that can support training DPR on like a pretty constrained GPU memory. So after we finish this DPR work, And in the NLP community, so DPR was originally proposed for open domain question answering. So after we proposed the DPR work, actually a lot of people actually try to extend DPR to many other different NLP tasks or other knowledge intensive NLP tasks. So this includes, like, for example, the fact checking. So basically, given a statement and given a large collection of documents, we want to check whether this the document collection can support this statement or not. So basically support or not supported. Some other applications also include like slot filling or knowledge-based construction. So basically, given a subject entity, given a relation, and we try to find what is the object entity that we should fill in for this actually particular relation. And also people have been extending DPR to an open domain dialogue. For example, given authors, I really love Granny Smith's apples. They are my favorite type of apple. And we are trying to build a dialogue agent that actually contains some information that comes from the knowledge source that can actually return as utterance to the input. So all these different NLP tasks have been actually framed as a knowledge-intensive NLP task. There was actually even a benchmark came out last year, actually, which is used as a collection of these tasks. So all this works actually essentially they start from the DPR and they try to fine-tune the DPR on a bunch of other downstream tasks. So we can also view this as a transfer learning from the question answering to other NLP tasks such as fact-checking or dialogue. Okay, so this is basically all I want to say about DPR. So moving forward, so last year in 2021, so we got really interested in a new problem we call it phrase retrieval. And we actually developed a new system we call it dense phrases for the phrase retrieval. So what is phrase retrieval? So here the goal is slightly different compared to DPR that is used to retrieve the text passages. Here our goal is to actually retrieve the phrases. So here the definition of the phrases is basically any segment of text up to L words. So in our implementation, we consider basically any segment of text up to 20 words. And in contrast, basically for DPR text passages, we just use a fixed size of text passages of 100 words. So here's one example. So if we have a question, who things don't stand so close to me? So we also use a basically one question encoder to map the question to a basically fixed size vector. And also for any phrases, basically any second text, for example, just the police. So it's just a phrase in this passage. And we use the phrase encoder to encode this phrase into a fixed size vector. But the phrases, there are way more phrases compared to the text passages, for example, in English Wikipedia. For example, if we consider all the phrases in English Wikipedia up to 20 words, essentially there are 60 billion phrases. So that means that we actually want to encode all the possible phrases in Wikipedia. And then finally, we can encode all the phrases offline, doing the offline indexing and using a phrase encoder. And then we can just do the nearest neighbor search. So before I talk about how we actually did the phrase retrieval, I want to talk about why we actually want to do the phrase retrieval. Given phrase retrieval, there are so many different phrases. Why do we want to do the phrase retrieval instead of the passage retrieval? The answer or the reason is actually because the phrase retrieval can actually achieve much more better runtime efficiency for question answering and other slot filling tasks. So for example, if we can think about this like family of the retrieval reader models I just described, so it's actually a two-stage model. So retrieval and a reader. So basically at the reader stage, at the second stage, the reader model needs to be implemented as a BERT model or T5 model. And we need to run the reader model on top of many passages. And this reader model could be actually very expensive. However, for the phrase retrieval models, essentially we can try to reduce this two-stage retrieval and the reader model into one single stage. So essentially we just need to do the retrieval. So basically, given the entire Wikipedia, we can just retrieve the phrases like the police from all the possible phrases that have been encoded in the text corpus. So if we can actually achieve this, So that means that we don't need the second stage of the reader, and this can be actually much faster at inference time. Okay, so next I would like to outline how the dense phrases is actually trained. As I mentioned, so DPR is basically only trained to actually retrieve from the 20 million passages. But dense phrases actually need to retrieve from the 60 billion phrases. So we actually overcome a lot of the technical challenges that I'm just going to give you the key idea of that actually behind this work. So the biggest idea of the dense phrases is essentially still to use a contrast learning. But instead of using the question and the passage as a supervision, in the dense phrases, we actually use the question and the phrase as a supervision. So phrase essentially just answer for question answering of other tasks. So essentially, we can just use the question and the phrase as a supervision. And we also propose a technique we call the pre-batch negatives, because this is actually a much more difficult learning problem. So we actually find that using actually many more negatives would actually help the performance by a large margin. So in the dense phrases, we propose this idea of called phrase batch negatives. Essentially, we try to use a lot more negative examples from the previous mini batches, but all these negatives actually come from the previous mini batches, so they actually still memories. So we actually don't backpropagate to this previous mini batches. So this idea is actually also very similar to the Mockle work in computer vision, but the biggest difference here is that because we have to train two encoders for the question and phrase, and we also don't do the momentum encode update to actually sync up the two encoders. And we also propose another idea in this work called query size fine-tuning. So this is actually very important. So essentially, we actually try to only fine-tune the query encoder while we actually fix the entire data store. So this actually is a very effective step to reduce the gap between the training and the inference. So if you are not familiar with technique, I encourage you to check out our paper. And finally, I also want to mention that another really interesting finding we have in the dense phrases is that we actually find that if we can use the phrase supervision instead of passive supervision, we actually find that the BM25 negatives are actually not necessary anymore. So we actually wrote a follow-up paper to actually justify why the phrase supervision can be actually act as a similar role as the BM25 negatives. Okay, so here is actually just a quick result of dense phrases. As you can see, like if you compare the DPR the retrieval reader work to the our dense phrases, the first retrieval work, we actually find that they can actually achieve very similar accuracy, like all natural questions, like 41.5 versus 40.9 accuracy. So accuracy could be actually very similar. So we actually made a lot of effort to also try to reduce the storage for dense phrases using some filtering techniques and also product quantization. So the storage could be also very similar. So what actually really make a difference is actually their inference speed. As you can see from the columns I highlight here. So basically the dense phrases can be actually much faster than DPR on both GPU and the CPUs. So it could be actually more than 100 times faster. So basically, after we developed this like a dense phrases work, we also built our repo, built like a demo to actually demonstrate how efficient this kind of phrase retrieval can be done. So if you have time to see this demo before, and if you're interested in phrase retrieval, I basically encourage you to check out our GitHub repo and also this demo to see to play these dense phrases. Okay, so I think I have spent like 25 minutes. Okay. Okay. So far actually I focus on like talk about learning retrieval for open domain question answering, and also for the other knowledge intensive NLP tasks using the question answering supervision. But in the last few years, the pre-trained language models such as GPT-3 have been quickly changing the NLP field. So in the last 1 or 2 years, we have been actually thinking about this question. Can we actually use the very similar ideas like retrieval-based ideas to actually improve the language modeling, to actually build better language models? So next, I would like to give you idea of one work that we actually have done very recently, and I'm personally super excited. So we try to build a model we call the retrieval augmented language models. So what is actually retrieval augmented language models? So for the standard autoregressive language models, essentially we just take a context. For example, Princeton University was founded in, and we pass this into a language model such as GPT-3. And the GPT-3 model is expected to predict the next word, which should be 1746. So for the retrieval augmented language models, the idea here is actually very similar to the retrieval models we built for open domain question answering. So here so we have a context. Princeton University was founded in. So instead of we only use the language model to predict the next word, which is 1746, we also build a large data store, which actually consists of the kind of key value pairs. So basically, the key is like a vector for the context, and the value could be one single token or could be a text passage. And then we can just do the nearest neighbor search using this large data store, and then combining this nearest neighbor search in the data store and also the autoregressive language model, we can actually combine the predictions to predict the next word. So recently, we actually wrote this new paper called Training Language Models with Memory Augmentation. And this approach is also called the TRIME. So TRIME stands for Training with In-Batch Memories, which is essentially a new training approach for language modeling. I think I'm just going to skip this, and I'm just going to tell you the key idea behind this TRIME training approach. So the idea is actually really inspired by the dense passive retrieval and dense phrases. So here the key idea is that the goal here is actually to train a language model. So the key idea here is that we want to maintain a set of the memories during training. And the training can be actually written as a form, as a set of context pair tokens. For example, the context could be Obama was born in, and the token, the target should be the next word, Hawaii. And it could be just a simple context, for example, Ross is, and the target should be the next word, the. And so again, the goal here is to actually predict the next word in language modeling. So when predicting the next token, give a context. So the idea here is that we don't just make a prediction only based on the output repetition. We also compare the context with the training memory that we built with a training memory. So here, the biggest rationale, the biggest motivation here is that the similar contexts actually are likely to have the same next token. For example, if you have two contexts, Ross is the author of the Divergent, or you have another context, Ross wrote. So basically, we found that these two contexts could be actually very similar. So there is a high chance that the similar context could actually have the same next token. So this is actually also the really big idea called distributional hypothesis in NLP. So this is basically the training objective we used in this TRIME language modeling objective. So essentially for context, for example, the context here is the Jobs became CEO of the fill in the blank. So essentially we are trying to align the context with two things. One is actually the token embedding, which should be the ground truth apple here. The second is we are trying to find all the other contexts in the training memory that actually share the same next word, which is apple in this example. So we find two contexts, return to apple or moves to apple. So essentially we try to make predictions based on both components, both the token embeddings and also other memories also other contexts in the training memory. So here is actually the training objective for our TRIME training approach. So the first component is actually very similar to the standard language modeling. And the second component is actually the basic one we added. Here is the training memory here. And we also use a hidden repetition to measure the similarity between these hidden vectors to actually capture how similar the two contexts are in terms of the vector space. And the testing objective is actually the same, except that we actually use a much larger memory at testing time. So here, the key idea is really that we change the training objective and we incorporate a very large memory set. during training, and then we can actually backpropagate to all the memory repetitions. And here the idea again is actually inspired by the DPR work. So for the positives, essentially we try to use a static token embedding, and all the contexts in the memory that actually share the same next token. And for the negatives, we also just use the in-batch negatives. Okay, so finally, one finally idea is that because we actually want to find context in the training batch that can actually share the same next token. So we actually also propose this idea, which is actually very, very crucial, that we actually try to group the similar segments of the training corpus in the training batch. And in practice, we just use a BM25 to batch similar segments of text in the same training batch. And then at testing time, we can just use the entire training set to build a memory set. And then finally, we can perform the nearest neighbor search. I think I'm probably already running out of time, so I actually encourage you to check out our paper. So basically, in the paper, we showed a lot of experimental results. We actually showed that using our a memory augmented language modeling training objective, we actually show that our training objective can be actually our approach can actually outperform the vanilla transformer language modeling by a very large margin by incorporating a very large memory set at testing time. And I also want to mention why we actually want to work on retrieval-based language models. So the first reason is actually the efficiency. So ideally, in the future, we actually really hope to build a very large data store and also much smaller encoder for the language modeling. And the hope is that this can actually outperform a very large language model such as GPT-3. And also another reason for the retrieval augmented language models is actually these models could be actually much easier to update and maintain compared to autoregressive language models such as GPT-3. For example, today, if we know that GPT-3 model was trained in 2020. If we want to update the training corpus from the 2020 to 2022, it's actually very difficult to update the GPT-3 model with actually less compute. But if we can build a retrieval augmented language model, it's actually much easier to update because we just need to change the data store. Finally, we also believe that the retrieval augmented language models can be actually much easier to deploy in privacy sensitive domains. So actually, I really have high hope that this kind of work, this line of research could have actually much bigger impact in the next few years. Okay, let me just summarize this talk. So in this talk, I talk about both the DPR and dense phrases. So DPR actually uses a question and a passage from the question answering data set as supervision. And dense phrases use a question and a phrase as supervision. And this kind of approach actually leverages the supervised data as the positives. And how to find the negatives could be actually a very important research topic. And this kind of approach can be actually very suitable for open domain question answering and other knowledge intensive NLP tasks. And I didn't get time to talk about another work that we did last year called SimCSE. Essentially, we actually proposed to use different augmentations of the sentence embeddings as positives to learn the sentence repetitions. So this actually could be actually more similar to the Sinclair and the Moco work in computer vision. And I also just talked about our new language modeling approach, TRIME, which actually essentially uses a context that share the same next token as positives for language modeling. So for this line of the research, essentially we don't actually rely on any supervised data, and then we just use the unlabeled text data as a way to actually formulate positives. So as I just described the way that we did in TRIME, and also I encourage you to check out the SimCSE paper. So essentially in this line of research, how to formulate the positive pairs will be actually the key ingredient to make things work. So actually my personal belief is that this can actually provide us actually new solutions for repetition learning of language in the next few years. Okay, I just have 2 more slides left. So I just want to quickly mention that for this line of research, right now we are still facing 2 key challenges. So the first challenge is actually the generalization problem. So there has been a lot of evidence, including one work we did last year, showing that the existing dense pattern retrievals or dense phrases still cannot easily generalize to the out-of-domain queries. But this is actually not a problem for sparse retrievals. So I know actually there are a lot of ongoing research that has me actually trying to address this problem. And the second problem is actually the scalability problem. So at least in the context of the NLP, today, the encoder size actually get bigger and bigger. But still, I just mentioned that the batch size could be still actually very, very important. So how can we solve this problem? Can we actually solve this problem using non-contrast learning techniques? I don't have the answer to that. And also another accompanying problem is that the data store size today can be also very, very large. So for example, this DeepMind paper actually used trillions of tokens for retrieval. So this is actually really a key problem for the kind of retrieval-based research. So another really important research question is, how can we actually speed up this kind of nearest neighbor search? Or even how can we actually store so many data points on like either CPUs or GPUs or over disk space in the future? Okay, so I'm just going to end here. Thanks for listening. If we still have time, I'm happy to take questions.
Thank you, Dr. Chen. Since we are running out of time, but we would like to take one question. Is there any question from the audience or online?
Yeah.
Please come here.
Yeah, you can speak into the microphone.
Yeah, thanks a lot for the great talk. So I have a question about, so recently I think from Jeff Dane's team, they show that the zero shot or few shot abilities of inference of the pre-trained large scale language model just come at a certain point when the data scale and model scale is large enough. So I just wonder if you have any insights on this retrieval augmented language model, like if they can compete with those large scale models on this kind of zero shot or few shot inference abilities. Thank you.
Sure, that's a good question. So I think that we are still at a stage that we showed that retrieval language models can be actually better than the autoregressive language models in terms of perplexity or in terms of generating fluent sentences. At least at the scale of the prime models of the millions of the hundreds of millions of parameters. So I think another key research question moving forward is actually how to use this kind of retrieval-based language models for downstream tasks, including the zero-shot inference, as you just mentioned. So there has been actually one work recently showing that they can actually use a prompt-based work, basically use the prompt to query the retrieval-based language models. They can actually achieve very good performance compared to autoregressive language models. But still, we don't really have the evidence showing that we can actually scale up this retrieval-based language models to like 100 billion of parameters. So I would say that's still an open question at this point.
Thank you.
Okay, thank you, Dr. Chen. Let's move on to the next speaker. Speaker is Dr. Eric Wang, who is an assistant professor at the University of California, Santa Cruz. He obtained his PhD from UC Santa Barbara. Eric Wang won the Best Student Paper Award at CVPR 2019. His work lays an emphasis on building embodied AI agents that can communicate with humans using natural language to perform real-world multimodal tasks. And more recently, he has also been working on fairness and bias in multimodal settings. And this will be the topic of his work, his talk today. And let's welcome Dr. Wang.
Thanks for the nice introduction. And it's really nice to be here today to talk about our recent work on fairness and privacy in vision and language models. And most recently, we have witnessed a new surge of deep learning models. And this time it started in the NLP area, such as the pre-trained language model BERT and GPT-3, and then the vision transformers in computer vision. And now it revolutionizes the area of vision and language. For example, the CLIP model, DLE model, and the Google's recent released Imagine model. So fact that we cannot deny is the data scaling law. Now we are seeing, right? The more data we have with more computer resources and a larger model, then we can achieve seemingly better and better performance. And back in 2017, we also observed this this finding in ICCV 2017 paper by Chen. And basically, the performance on vision tasks also increases linearly based on the volume of the training data size. But can data go wrong besides the performance boost? First, large-scale data set also introduce some bias issues, which often represent our stereotypes, human stereotypes. And the model trained on biased data exaggerate such bias and lead to serious fairness issues. And second, the data represent our world, and there could be a data privacy leakage issue, and then it would result in information leak and misuse. So in this talk, we will mainly discuss our recent efforts towards those two directions: fairness and privacy. And although the data set do have a lot of bias, but our focus here is to resolve the model bias towards a fair vision and language learning model. And the first work I'm going to introduce is our EMLP paper last year. Okay, let's look at an example. Okay, so this is the Google search results. And the question we would ask is, are gender neutral queries really gender neutral? For example, a person is playing basketball, right? There is no gender specific words in this sentence. The person is totally gender neutral. However, when you search this query in Google search, then it would return you such results. And as you can see, only 1 out of the top 5 returned results is actually depicting women. And how about our machine learning data set and models? Okay, so now we can choose the well-known model CLIP on the data set Flickr 30K. And now we can use the search query. A person is cooking, which is also gender neutral. And as you can see, only 2 out of top 10 images are depicting women in this case. Google search is essentially a text-to-image retrieval task, right? And such biased search results would worsen human stereotype. Okay, so to resolve this, let's first have a little bit introduction of the image search model or the image to text retrieval model. So basically we have a text query and an image. Then we use an image search model to calculate the predicted similarity score between those two. And then image search model basically aim to retrieve the top key images with the highest similarity scores. And to solve this issue, first we need to define the gender bias issue in this setting. And we need to know the gender attributes of images. And here we classify the gender attributes of images into 3 categories: male, female, and gender neutral. I'm sorry that we only consider the biological sex of humans. Okay, so basically when there are only men in the image, we consider this image as a male image and otherwise a female image if there are only women in the image. And if there are no people or a group of people, including both man and woman, then we consider it as a gender neutral image. And in order to quantify the gender bias image search, here we define the gender bias for each text query. For each text query, the model would return us the top key results. And if the number of, there is no gender specific images, then the gender bias is 0. Otherwise, we use the relative gender difference as the gender bias for this specific text query. And the gender bias over the whole data set would be the average of the gender bias for each text query. And here key is the number of retrieved images for the given text query. And there are two fashions of machine learning models for the text to image retrieval task. First is the domain-specific models, the old-fashioned one. We can train specific image search models on the target data source. And the second is general purpose pre-trained foundation models, which is often pre-trained on enormous image and text data available online. We propose 2 treatments for both type of models. And for the specifically trained models on the in-domain data set, we propose a fair sampling strategy. As we know, the bias typically comes from data imbalance. As imbalanced gender distribution in training data leads to such gender bias. So contrastive learning is often used for this image text matching problem. Here, instead of random sampling or some other type of sampling like hard negative sampling, we aim to sample negatives equally from male and female images for gender neutral queries. And the intuition is to downplay the gender information in contrastive learning and avoid some unfair leverage of it. And for some general purpose pre-trained foundation models such as CLIP, we propose a post-processing debiasing method, feature clipping. And the idea is that different feature dimensions contains uneven gender information. And therefore, we can project the pre-trained representation vector onto the subspace that are not correlated with gender information. And then we can use those projected information to do the image text retrieval. And this is a very simple approach. Okay, suppose we have a pre-trained embedding feature vector here, and then we can estimate their corresponding mutual information with the sensitive attribute, and in this case, it's gender information. And then we find the feature dimensions with the top key mutual information and clip them. We throw them out and use the remaining feature vector to do the text image matching. Here are the results on 2 popular data sets, MS Coco and Flickr 30K. Scan is in-domain trained model. CLIP, as you know, is the pre-trained vision and language model. We report both the bias metric and the retrieval performance, the recall score at top 10 results here. As you can see, our methods, both fair sampling and feature clipping methods, can achieve better bias results while maintaining a comparable retrieval performance. As you know, there is, for the fairness works in the machine learning community, there is always a trade-off between accuracy and fairness. And here we achieve optimal trade-off between the bias metric and the retrieval performance. And note that the bias recall trade-off is controllable in both debiasing approaches. We can control the hyperparameter to account for that. We also tested on a real-world Google search dataset, occupation. This dataset is introduced in 2015 by some HCI people. Basically, they use some keywords of occupations to search on Google, and then collected the top 100 returned results. And then ask humans to label those images for them. Okay, here are the results between clip and clip with our feature clipping methods. Okay, so the orange bar represents the bias towards women, and the blue bar represents the bias towards male. And as you can see, the bias is significantly reduced when we prune the top 100 features that are correlated with the gender information. All right, so yeah, that is sort of a case study, targeting at the gender bias issue in the task of text-to-image retrieval. How about other fairness dimensions such as race and age or even language? Okay, so next I'm going to talk about a new research direction, multilingual fairness issues in multimodal representations. Okay, so we have the CLIP model, and CLIP is trained on the English corpus and can be naturally applied to those downstream English, vision, and language tasks, and even image recognition tasks. And we could also adapt it to conduct those tasks on different languages other than English. And to do that, we can simply replace the text encoder with a multilingual text encoder, such as multilingual BERT. And then the textual representations in English can be desiredly transferred to multilingualism and support promising downstream multilingual tasks. But here are the questions we would like to ask. Do multilingual models, such as multilingual CLIP, treat languages equally? Are their performance biased towards some particular languages? And here we would like to view language as a fairness recipient, just same as gender, race, or appearance. And then we define two multilingual fairness notions, multilingual individual fairness and multilingual group fairness, in order to evaluate multilingual fairness. Okay, so a little bit background about the fairness criteria in machine learning. There are two fairness notions in the machine learning community, individual fairness and group fairness. For individual fairness, we expect that the outcomes of similar individuals should be treated similarly. And for group fairness, we expect the rates, such as the accuracy or other metrics, the rates between different sensitive groups should be equal. For example, the male groups and female groups, the Asian groups, white groups, and black groups. Okay, so how do we contextualize those fairness notions in multilingual representations? We could use images as the visual grounding between different languages. And then for individual fairness, we expect that text in different languages should be equally similar to this image. All right, so we can calculate the similarity between the image and the query in English, French, and Chinese. Then the similarity scores should be similar in order to satisfy the multilingual individual fairness. Okay, so here is the official definition. A model M satisfies alpha multilingual individual fairness if for any image tag tuple, an image, text query in one language, and a text query in another language, we have, the similarity gap between image text queries is bounded by the similarity gap between those two text embeddings in different languages. Okay, and so then we wonder, how individually fair are those multilingual representations? Okay, here we conduct some experiments on the multilingual Flickr 30K dataset, which contains English and German captions for images. And here the x-axis represent the text similarity gap in the pure text space. And the y-axis represents the similarity gap between those two image text pairs. And the slope represents the alpha coefficient. And here we visualize the empirical upper bound on the data sets and the theoretical upper bound, which you can see the proof and the derivative in our paper. And basically, the conclusion is that multilingual representations actually satisfy individual fairness. But can individual fairness guarantee group fairness? Then we evaluate the performance, the accuracy of those two languages and between English and German captions. And as you can see, the top one accuracy disparity is very large. So individual fairness does not prevent accuracy disparity among languages. So if this is a very interesting observation, because in the machine learning community, there are some researchers that assume if you solve the individual fairness, then the group fairness issue would be naturally solved, but that's not the case. Particularly, that's not the case for vision and language models. Okay, so then we have to, find a way to evaluate multilingual group fairness. First, we define multilingual accuracy parity. So basically, the accuracy rates of the model M on different languages should be equal. For example, here, given this image, we have the ground truth caption, a photo of a cat, and a false caption, a photo of a bunny. Okay, so we can calculate the similarity scores between the image and those two captions. And in this case, the ground truth English caption received the higher similarity score. So we did it right. While, in some other languages, it may not be the case. For example, in French, so the false caption actually received a higher similarity score. And okay, so in those Chinese captions, photo of cat, the true caption received a higher score. As you can see, there is accuracy disparity for this specific case. And we calculate the accuracy disparity of the whole data set to evaluate multilingual group fairness. And we test the performance of the multilingual clip model on two tasks, gender classification and race classification. And as you can see, among 8 languages, Chinese, English, French, German, Japanese, Russian, Spanish, and Turkish. And as you can see, there is a severe multilingual accuracy disparity among different languages. And we are also curious about, some multi-dimensional fairness issues between different fairness dimensions, including language, race, gender, and other sensitive attributes. And so we define the group rate gap in a single language with respect to group A and B. So for example, they could be male and female in English. Then the gap between male and female groups in English is defined like this. And then we define the group dependent rates between different languages, which should be equal to satisfy the multilingual group rate parity. And here are some results. Okay, so here are some multi-dimensional results with respect to different fairness notions, races, genders, and languages. Okay, there are more results in the paper, but here I would like to point out a few interesting findings. First, English and French achieved accuracy parity for white group. And Black and Southeast Asian groups suffer significantly gender disparity for all the languages. The y-axis is the accuracy gap between male and female groups. All right, so here is the summary of multilingual fairness issues. So we basically introduced two fairness notions in the multilingual multimodal setting. And for multilingual individual fairness, we expect that text in different languages with the same semantic meanings are equally similar to the same images. And for for multilingual group fairness, we expect equalized accuracy rates across different languages. A few takeaways. Vision and language models are very powerful, but they can harbor biases. And fair sampling can mitigate bias in contrastive learning during training. And feature clipping is a very lightweight debiasing approach on pre-trained representations during inference. And we can also view language as the recipient of fairness notions, and visual grounding provides a universal way to evaluate multilingual fairness. And several bias issues are observed on gender, race, age, and language, and need some further treatment. Okay, so in the remaining lecture, I'm going to quickly introduce our recent work on preserving the privacy of the data. If the data privacy is not protected, then there could be a very serious information leak and the misuse issue. Especially when we deploy a embodied agent inside our house, right? Okay, so let me first introduce the embodied agent task, vision and language navigation. Okay, suppose there is a robot deployed in your house, and then you could, ask the home assistant robot to do some households for you. And like, can you grab the coffee or the plant for me? Then, the robot may ask a follow-up question like, where is it? Then you could provide some detailed fine-grained instruction for the robot to execute. Get out of the room and go towards the kitchen. The plant is on the window near the kitchen. Then the agent would understand your instruction, interact with the environment, and navigate in the room, and finally reach the location and pick up the plant for you. But recently there are very fast development of vision and language navigation. We have observed a bunch of new and advanced methods towards better and better performance. However, there are some obvious privacy concerns involved. First, the training data privacy. So right now we rely on some simulation environments to train the agent. And to do that, we have to scan the individual rooms and houses and centralize those data in a server for training. So as you can see, there is a serial training data privacy. And some users or some homeowners may not allow you to do that because they care about their privacy, right? And also, once you deploy a robot into your home, especially the one with a camera, then it could observe everything that could happen in your house, like the human activities, your house layout, and and the sound and everything. So there is also a serious inference data privacy if we allow the agent to update the observed data into the cloud server. Okay, so we propose a privacy preserving federated VLN approach to address those issues. And as just discussed, typically for VLN learning, we centralize, all those information, all those environments and the data collected within those environments into a server, and then train a model on this server. So here we could actually view each house environment as a local client, and then we have a client model, local client model, to learn and interact only with the information within this environment. And then we could do upload on nothing other than model updates, the gradients into the server for global aggregation. And this is federated VLN learning. Okay, so in vision and language navigation task, there are two learning scenarios: scene environment training and unseen environment pre-exploration. For scene environment training, it's a pretty standard machine learning scenario. You can train a generalized model on scene environments and then directly test it on unseen environments. And for unseen environment pre-exploration, we basically allow the agent, after deployment, we allow the agent to pre-explore the unseen environments and get familiar with the house and therefore adapt to the new environment. Okay, so we propose in our Fed VLN approach, we propose two methods for those two learning scenarios. First, decentralized federated training for scene environment training. So here we view each house environment as a local client. And then we have this local client only deals with the data within this certain house environment. And those clients upload nothing other than model updates to the server. So there is no data communication between client and server and between different clients. By the way, the speaker model used for data augmentation in VLN is also trained via federated learning. And for pre-exploration, there are primarily two pre-exploration techniques or schemes. Centralized pre-exploration, where we would like to centralize all the pre-exploration data at the different houses into one server for joint learning. And then environment-based pre-exploration, where the deployed model only pre-explores and adapt to the local environment where the agent is deployed. And as you can see, there is no privacy protection in centralized pre-exploration for sure, because we always upload those local information onto the server for learning. And the environment-based pre-exploration probably has the best privacy, as it only adapts to the local environment and never uploads anything to the server. And here we propose a federated pre-exploration, which obtains better performance than those two approaches while maintaining a good privacy protection. Okay, so this, we don't have much time for this. I would quickly overview this. So language understanding is rather general. So here we only share the language encoder with the server for federated learning, but adaptation is very important. That's why environment-based pre-exploration has better performance than centralized pre-exploration. So we let the other modules do local adaptation without sharing. And we test our methods on 2 baseline models, environment job and clip-based VLN model, and 2 datasets, room to room and room cross room. Okay, so this is the result of decentralized federated training on R2R dataset. And as you can see, our federated learning algorithm can achieve comparable results on the ANSI environment, if not better, while maintaining the data privacy. And actually, the federated learning algorithm achieved better performance on environment job and comparable results on CLIP VRL. And this is the results on the cross-room data set. We observed the same trend on success rate, SPL, and CLS, both goal conditions evaluation metric and path fidelity evaluation metric. Our federated training algorithm achieved comparable results while maintaining the data privacy, the training data privacy. This is the result on federated this is the result of federated pre-exploration compared with the other pre-exploration algorithms. And as you can see, the federated pre-exploration algorithm actually achieved the best results. And so centralized pre-exploration is the least private algorithm because it shares all the data. And environment-based pre-exploration is the most private algorithm because it shares nothing, but the performance is not as good as federated learning. All right, so here are the conclusion of this work. We designed our study the data privacy issues in vision and language navigation with respect to learning scenarios. The decentralized federated training algorithm achieves comparable performance while protecting the same environmental privacy. And the federated pre-exploration achieved a good performance privacy trade-off, the best performance while preserving unseen environment privacy. And in the future, I think since this is the first study towards private preserving embodied agents, but federated learning itself is not entirely private. You can design some adversarial attack to do some membership inference, like to determine whether this image belongs to that environment or not. So we would like to develop some, more robust technique to defend this kind of adversarial attacks. And different privacy could be the way to go. Thank you very much. And I would like to take a few questions if there are time left. Yes.
Yeah, so this is a question about your slide on individual fairness, where you showed that you can have an image to ground similar meaning sentences in 2 languages.
Yeah.
But so there are many cases in some in language where sentences might mean the same thing, but the words that are used individually might mean the different things. So let me give you an example. Hello, ni hao, namaste. Okay, so these are 3 hello words in 3 different languages. But ni hao means you good. Namaste means I salute you. So these individual words are very different, but the way we use them is very similar. So is it fair, or is it always good to have like identical similarity scores for words which mean different things?
I see. That's a good question. But here we considered the semantic meaning of the entire sentence. So we do not.
So would that affect? So I mean, because you would move your model to certain points where you're basically driving the model to a location where these sentences mean similar things, but would that affect performance on the individual words?
Yeah, so I think that's a very good question, and we did not test on that. As
this is an edge case, but I just thought about this.
And yeah, that's something we should explore, like those whether the semantic meaning of the entire sentences, the sentence level meaning could influence the word level meaning. Yeah.
Awesome. Any other?
So actually, the bias in the data sets, not just in the model. So if you train the model with a already biased data set, then definitely the model might preserve some bias. So what do you think about the bias in the data set?
Yeah, that's a good question. I think all the data sets are biased. Even the best balanced data sets are biased. And if if you look at, there is a EMRP best paper in 2017, where they basically show even if you try very hard to unbias your data set, then the model trained on such balanced data set is still biased. So because there are a lot of implicit bias that you can not manually fix. Right? Yeah.
Okay. Then how about your proposed like the matrix? You have the matrix how to define the gender bias. Use that matrix to balance the data sets. Will it be helpful?
Yeah, so you mean that we can use
some explicit matrix to make the data sets less biased?
Yeah, so as I said, even if you try very hard to balance the data set, like to keep the data set with half male images and female image, but it could still result in a biased model, because there are some implicit bias that cannot be easily identified by humans. Like for example, in an image, a woman could have a particular style outfit, other different than males, and all those things could result in biased search results.
Okay, thank you. Oh yeah, sure. We have one more question.
Thank you so much. Thanks for the great talk. I just wonder if you see like the performance. What is the performance change if you evaluate the bias model on some regular data sets, like just a regular image to text retrieval, those kind of things?
Yeah. The results we are presenting are on some regular data sets, MS Coco and Flickr 30K. Those are the standard data sets.
The metric is specially designed for.
Okay, so let me show you. We actually evaluated the performance of our methods in terms of two metrics here, the bias metric and the retrieval metric. The recall score. And the recall score is sort of the standard metric for image text retrieval.
Oh, okay.
Yeah, there is certainly a trade-off between bias and retrieval performance, but I think our method maintain a good trade-off.
I see. Thanks a lot for the clarification.
Thank you. Thanks.
Yeah. So this is the first part of
In our case, we start from an image caption pair. First, we mask a token in the caption, and then we try to retrieve the masked token using the remainder of the caption and the image. In this example, we would like the model to leverage the visual representation to predict the word umbrella. So now that we've defined the proxy task, we propose a multi-modal architecture to tackle it. Our model requires a visual representation. This is what we're really interested in. The rest is just a pretext. We need a textual representation. We assume it's provided. For example, we can use the BERT model that I mentioned in the previous slide. And the model also needs auxiliary modules to solve the task. We call this proxy task image condition mask language modeling, or ICMLM for short. And rather than quantitative results, because we don't have lots of time, I would like to show you visual attention maps that are produced by our model for a given image caption pair, as we mask different tokens. So we see that as the mask token varies, the model can attend to different image regions depending on the mask token. We experimentally observed that ICMLM produces representations that transfer as well as the ones produced by self-supervised learning, at least the one that were available at the time of this work, and using 10 times fewer images. Our piece of work was obviously not the only attempt at learning visual representations by leveraging text. And I'd like to spend a couple of minutes positioning it in the vast literature. Again, I won't be able to be fully exhaustive, but I want to give a few key references. The very first attempt at learning visual representations using captions dates back from 2007, where Ariadna Poitoni and her team created and solved auxiliary prediction tasks using some images and their associated captions. 10 years later, this task was revisited by two notable contributions. In the first one, label sets are constructed out of caption n-grams, and CNNs are trained to predict those labels. In the second work, topic models are extracted for Wikipedia pages, and CNNs are trained to embed images in this topic space. Almost concurrent to our work, the Virtex approach was presented at CVPR 21. It uses the exact same data sets and proxy task that are ICMLM. And of course, the CLEAP model needs no introduction, and it has pushed the idea of learning visual representations using captions to a scale without precedent. And since then, there are also many other works that have been proposed that also build on this idea. Now let's move to the image retrieval task, and let's focus on particularly complex retrieval tasks. You all know this, but when a user would like to interact with a large image collection, one intuitive way to retrieve relevant information is to provide an example image of the desired results as a query. This is a task that we all know as image retrieval. And being able to query a database with a single image is very convenient. Yet, visual queries can be ambiguous. Let's take the example of that painting. If I query with that painting, I'm most likely looking for similar paintings of the same style, maybe of the same painter, but I'm probably not looking for something like that, right? And yet, I would argue that this result is very relevant visually, at least at the local level, than the query image. So how do we deal with this ambiguity? Well, one thing we can do is to inject prior information. This was mostly done for the earlier or more standard approaches, where a pipeline was designed that enforced reasonable properties, such as invariance properties or geometric consistency assumptions, things like this. Or one can leverage training, and you can train on a representation set of examples provided by the users. And that's mostly what is done by the deep architectures nowadays. And also to reduce this ambiguity, in most of the retrieval works, the problem of the ambiguity of the query is reduced by assuming that in the retrieved results, you would like to have the exact same object as the one contained in the query image. And this is known as the instance level retrieval task. In other cases, we assume that we would like to retrieve instances of the same fine-grained classes. And this is something very common in the deep metric learning literature. But today, I'd like to focus on queries of this type. Assuming that I query the system with this image, where you have these two persons, most likely a little girl with her father playing the football together, you're probably not looking for the exact same ball or the exact same t-shirt, right? You're most likely looking for images like this that can be arguably quite similar, but I would say that they tell the same story. This is what I'm going to introduce as the semantic image retrieval task. And this is a piece of work that started being quite a few years by now, but I think it's still relevant for the discussion we're having today. So let's look at this semantic image retrieval task. And the first question that you may ask me, and that of course we ask ourselves when we start this project is the semantic retrieval task even well defined? Because it sounds like a subjective task. And yeah, of course we verified that, and we collected human annotations where we showed people triplets with a query image, two potential results. And we asked people which of the two was most similar to the query. Well, as you can see, when we collected the results, people didn't agree 100%. And that makes sense because it is a subjective task. But like our annotators agreed most of the time, as can be shown by this leave one user out agreement score that reaches almost 90%. The second question that you could ask is, well, what could capture semantic information so you can predict if two images are semantically related or not? And we conducted a study on the visual genome dataset, which is very nice because it comes with plenty of different types of annotations. And well, I'm going to skip the details, but long story short, we observed that the region descriptions, so in other words, the captions, were what best captured the semantic information and what were best able to predict if two images were considered semantically related by the users. Again, that's very convenient, but you cannot assume that you have captions together with your images all the time. So can we learn a visual representation that is compact enough to perform retrieval, but that is also good at predicting this semantic relatedness? And that's what we worked on, assuming that at train time, we do have human captions, and we're going to use them as privileged information and as a proxy for the semantic similarity that we would like to use as a grand truth. So what does it mean? It means that if we have these two images with fairly different content visually, you can look at the captions, and the captions are fairly similar to each other. So you can tell that these two images are semantically related. We're going to use this information to train a visual representation, so to train an embedding function in a semantic representation space that is going to make sure that the two visual representations of two images with similar captions are going to be close in the embedding space and far away from an image which is dissimilar according to the captions. And once you've trained this semantic embedding space, if it's any good, at test time, there's no caption whatsoever. So you can embed purely visual information from your database. You can embed your query, and you just look for the most related image according to the semantic representation you just built. So how do you build this semantic embedding space? Well, any ranking function would do. And in our case, we simply use the triplet loss, but you could use anything else. Here in this triplet loss, we assume that we have a query image, a relevant image for that query, and a non-relevant image. And we make sure that the similarity between the query and the relevant image is stronger than the similarity between the query image and the non-relevant one by a margin. So that's how we can build this semantic embedding space. And in this version, the captions are only used to decide if two images are semantically related to each other. Although we have no text at test time, we could still decide to build a textual representation of the corresponding caption that would also represent text in the same semantic representation. So in this joint embedding space. And I'm going to show you in a minute what this can be used for. So let's look at a qualitative result. Let's assume that I query the system with this image of this couple at a wedding cutting a wedding cake. If you use baseline representation, for example, pre-trained on ImageNet, these are the results you get. So you have images that are, I would say, fairly similar. You have people, you have the same objects, plates, maybe a tie, but they're not exactly telling the same story. After training, in the way I just showed, you can see that your results that, in my opinion, are much more related to the query. We can see pictures of couples again in a formal setting, and even in some cases, cutting a wedding cake. Let's take this other example. If we query the system with a semantic representation with a picture of a man riding a horse, you can get more images of men riding horses. But now, because I've built a representation space that can also accommodate it for text, you can start embedding the word horse and embed the word elephant and do a little bit of arithmetic in this embedding space. And you can get results like this. Pictures of person riding elephants. So of course, this is kind of cherry pick. It doesn't work as well for every single cases, but this is to show you that you can start reasoning in that representation space. And I'm going to show next a more principled way to have these multimodal queries. So to summarize this, this piece of work, we've defined the task of semantic image retrieval. We've seen that the task is properly defined because there's a large interhuman agreement. We've seen that human captions are a good proxy to predict that two images are semantically related. And we've seen that we can build a good visual representation for this task using the captions. Now let's go back to our task of image retrieval. And let's assume that we want to refine the query exactly as we did in the last qualitative by providing text. For example, I'm looking for images of the Eiffel Tower in the sunset. That's what I'm going to call image retrieval with a text modifier. And I'm going to show a piece of work that specifically looks at the garment retrieval problem. This is a piece of work that we've presented at iClear not so long ago. So let's go back to my garment retrieval example. Let's assume that I'm looking for a dress. Following image retrieval, I can provide an example image of that dress. But maybe I don't know exactly what I'm looking for, or I don't have a photo of that dress. In that case, I could provide a textual query, as is done in cross-modal retrieval. Yet it's very tedious to describe with words every single aspect of the dress I'm looking for. One way to solve this, which is the one we're interested in here, is to provide an example image, but explicitly specify with text what should be modified. Here, the color of the dress. In this setting, the query is bimodal and composed of a reference image and a text modifier. The reference image provides strong visual context for the search, while the text modifier specifies how it should be modified in order to find the desired target image. Standard approaches for this task typically fuse the features of the two components of the query into a single representation, so it can be compared to the representation of any potential target image. More complex approaches exist, but they typically do not scale well. Here, we advocate for a lightweight combination of the two components of the query in a way that takes into account their specific relationship with the target image. Our approach is composed of two modules. The first one draws inspiration from visual search and compares the reference image with the target image. Yet, directly comparing the features of these two images is inaccurate, since the two images should differ based on the modifying text. Hence, we use the text feature to guide image similarity with a lightweight attention mechanism. Intuitively, the text-guided attention AIS reweights the dimensions of the image representations to focus on shared characteristics. The second module draws inspiration from cross-modal search and compares the text modifier to the target image. Indeed, the textual cue explicitly describes mandatory details of the target. However, directly comparing the features of the modifying text and the target image is insufficient and even potentially detrimental, since part of the target image should stay similar to the reference image. So again, we use the text to gauge the dimensions of the target image feature before comparing with the textual feature. And one last thing, the textual modifier and the target image are from two different modalities. So we first project the text feature into the visual space using a learned linear transformation. The final similarity score for ranking is simply obtained by summing both the implicit similarity and the explicit matching. I'm going to show a few qualitative examples obtained with this Artemis method. If we query with this shoe image and ask for colorful trims, we get such results. Similarly, we would like this dress to be instead brown with long sleeves and a U-neck. We see that the retrieved results comply with the text requirements. When key information is missing from the text, visual information comes from the reference image and it's preserved. For example, the dress length or the presence of lace in the shoes. Now let's move to a more standard way to query for images. In most search engines, you use a textual description to look for images. And this is often called the text-to-image retrieval task. This is a highly studied task, but purely textual queries are typically ambiguous as well. For example, let's make a quiz. Each of the 4 captions that you see on the right correspond to only one of the 4 images on the left. Can you match those 4 captions to their respective image of the COCO dataset? As you can see, the task is impossible even for humans. Yet many approaches still learn embedding spaces which try to match representations of each image with a representation of all its captions. One solution to this problem is to relax the constraint and to explicitly model the ambiguity of these pairwise associations using probabilistic embeddings. And this is an option that we considered in a piece of work we presented at CVP of last year. Another option is to reduce the ambiguity by leveraging the text that can be read in the visual scene. So this scene text provides additional information that can guide the retrieval task. And this is what brings me to the last piece of work that I'd like to mention today. It's a piece of work that we presented at WAGFI last year. So let's assume that our query here is the sentence, a group of people eating pizza. Which one of these 2 images best correspond to the caption? By just looking at the images, you could say that both images are very relevant because it's impossible to tell what those people are eating by just looking at their plates, right? So yet there's a clue that can be found by looking at the name of the restaurants. And we can see that one of these names matched the food better. So with a visual representation that can consider both purely visual cues, but also the scene text, the task can become much easier for this particular caption, right? So we introduce this task as scene text aware cross-modal retrieval. To be able to study this task, we created a benchmark, COCO text captioned. And this benchmark, it's benchmark that we call CTC for short. It's at the intersection of the COCO caption dataset and of a filtered version of COCO text, keeping only images whose text is legible, but also machine printed. In the end, this gives us a dataset of 10,000 images, where each image contains the 3 modalities: images, captions, and scene text. We also proposed an architecture that can solve this task. It's called StarNet, and it's a tree model, and it extracts local features and also generates semantic relationship with graph convolutional networks by combining region proposals for visual features, OCR predictions for scene text features, and the GRU representation for caption. Here are some qualitative results. Let's take, for example, the 3rd row. We see here for the caption, China airliner is parked as an airport near another jet. We see that the name of the airline clarifies the query and allows to rank the results among all the images containing planes, with some that are more relevant to this particular caption. I think that's an interesting task. And if you're interested in the task as well, I encourage you to consider our benchmark. This brings me to the end of the talk. I've covered different tasks that use image and text. We've only scratched the surface of everything that is interesting and that involves the image and text. But if I had to summarize the different parts in a few take-home messages, a short take-home summary, I would say that textual descriptions are really good tools to train visual representations. We can train these representations from scratch using text prediction as a pretext task, or we can refine and specialize existing visual representations, for example, to complex image retrieval tasks. We've seen that text can be used in image retrieval to refine visual queries because they're very useful to bring a lightweight attention mechanism. And we've seen that incidental text or scene text appearing in images can be extracted and combined to the traditional visual cues to remove some of the ambiguity in retrieval. Of course, there will always be ambiguity left, but this is one step towards solving it. So thank you very much for your attention. Here are the main references that I covered in this presentation, and I would like to take this opportunity to thank all my amazing collaborators that I'm extremely lucky to work with. And now, if there's time, I would be glad to answer any question.
Okay, thanks, Dr. Larlus. So we can open up for questions from the audience in person. I see that there's a chat. Okay. Yeah. Any questions? Or I can ask a question. Okay. So I really liked your slide which showed the ambiguity in retrieval with the baseball example. So I was thinking about common sense. So like there have been image captioning work or like visual common sense reasoning as a VQA task where the goal is to predict something that is not visible. So what is the person thinking? So is there a way that we could also retrieve images or retrieve text beyond the visible entities like actions and objects? Do you have any thoughts on that? So for example, an image for the caption, a person is thinking about eating a pizza. What would that look like?
That's a great question. I agree that this image text association and learning from that is just the beginning to start reasoning about complex scenes. And we've seen that there's more and more models that are trying to incorporate multiple tasks. So learning about certain tasks will help for others, right? And we have these more generic approaches that are going in this direction. And I agree that the next step for solving this task and reducing the ambiguity would be to start reasoning with these external modules that understand common sense and like potential interactions with objects and scene better. Yeah, I agree.
Okay, great. Yeah, one more question.
Hi, Dan. Thanks for your great talk. And I really like the part that you talk about the multimodal query retrieval. That's one main focus of this workshop. So I would like to hear your opinion about like what's the current limitation of the system on this task and what should we focus on improving in the future?
That again is a great question. I think one of the limitation is the ambiguity of the user intent, because these data sets, they are acquired with the user looking for something very specific in mind. And part of the query is obviously described in the text, and that is explicitly mentioned in cues. And there's also one part that is a lot more ambiguous because it's implicit from the example image. And in my opinion, there's no way we can start having more accurate results for concrete application without personalizing a little bit for the user. So maybe with having like a few iterations and a user feedback in the loop, or personalized models that would start building into multiple queries, a series of like interactions between a particular person with such a system, such a retrieval system. So I think to really push this task further and improve tremendously the results, we would have to start reasoning with multiple queries altogether. Well, that would be my answer. That would be my opinion. There are also many other directions, right, that are extremely valuable and very interesting. But that's one that I think would bring the next step towards making such a system very, very easy to use for the actual end user.
Okay, thank you. Yeah, we have one more question. Please, Ken.
Hello, I just have a question. I think you have a slide talking about their straight caption all can describe one images, but I just wondering about a detailed math, and I see you most of the training you're using the triplet loss, and the triplet loss you need to define a positive pairs and a negative pairs. But I just wondering, in that case, how do you train? Are you still using the triplet loss, or are you training with other method?
So I don't know if you were referring to a certain piece of work. So I would say that I'm using, like, I showed the triplet loss for the semantic image retrieval piece of work, right? And there are obviously other ranking losses that you could use that would also help you rank. But no matter what you use as a ranking loss, you need a way to define what is relevant to your query and what is non-relevant, or at least rank from the most relevant to the least relevant. And at the moment, we have no other way than relying on the annotations we have, which are the captions that are being provided by users for a particular image are all relevant. And everything that has been written for another image is non-relevant, right?
Yeah, can you go to a slides? You just show there are three captions all can describe one image. I think that there is a slide.
Is that for
yeah,
cross-modal retrieval?
Yeah.
I see. Okay, I think the one you mean
sorry,
this one, right?
Control.
This one. Is that the one?
Yeah, this one. Yeah. Okay.
Okay, great.
Yeah, this one. I just how did you train with this case?
How do we train with this case? So in this particular case, if it happens that this image is chosen in the batch, we are going to use these captions that have all been provided by users as ground truth for something relevant to that image.
Okay.
And then we're going to use captions that have been used to describe other images as negative examples.
Okay, and all these three captions are treated as a positive, right?
Right.
Okay.
This is a very standard way of training cross-modal retrieval models. And that's one of the things we are arguing against in this piece of work, right? Where I try to model the ambiguity by learning the actual uncertainty associated to each of these data points in the embedding space.
Okay, thank you.
Does that answer your question? I'm
Yeah.
sorry if I misunderstood it. Please reach out and we can chat and let me know.
Okay. Maybe we can chat more detail offline. But I think the current answer is good. It's good to me.
Okay. Thank you. Thank you for your question.
All right. Thank you, Dr. Larlus.
Thanks a lot.
Thank you. So our next speaker is Dr. Aniruddha Kembhavi, who leads prior the computer vision group at Allen AI. He's also an affiliate associate professor at University of Washington. So he received his PhD from UMD, and his research spans vision and language, embodied AI, AI for social good. So more recently, he's made a big contribution to unifying multiple vision tasks under under a single roof and towards general purpose vision, which is the talk for today, which is the topic for today. And we're excited to have him speak at ODRUM. So over to him. Thank you.
Okay. These are fantastically powerful models, but you can't easily take them and adapt them to do a new task. You'd have to add new parameters. You'd have to completely change the architecture. Of course, there's also been, startup trouble. There's also been a lot of progress on multitask models. So models that can perform more than one task. So for example, MaskR CNN can do detection and segmentation and key point estimation. But these multi-purpose models, while quite powerful, are sort of static. They're designed for some end tasks, and they can do those end tasks really well. But once again, if you want to move to an N+1 task, you're going to have to change the architecture. You're going to have to understand the details. You're going to have to make modifications. So our research is directed towards how do we take the next step? People have gone from single task to multitask. How do we go from multitask to general purpose models? General purpose models where the number of tasks a model can accomplish is extremely large. And importantly, if you want to perform a new task, you don't really have to know the details or the underlying architecture. You should just be able to give it some data, and then it should be able to fine-tune itself to this new task. And so in this talk, I'm going to talk about the 3 tenets of general purpose vision systems. These are sort of 3 guiding principles that we think about when we're designing these systems. And then I'm going to talk about 3 general purpose vision models that we've created over the last, I would say, about a year or 18 months. So let me start with the tenets of general purpose vision systems. So there are 3 tenets that we are following as we design these systems: generality of architecture, generality of concepts across skills, and generality of learning. And I'll go through these in a little bit more detail. So the first one is generality of architecture. So when we think of vision systems, we're trying to build very, very general purpose architectures that can support a wide range of tasks once this architecture is designed. And importantly, if you have new tasks that you want to build, you shouldn't really have to change the architecture. You should not have to add any new parameters. And here we're motivated by biological systems. So biological systems, whether it's human beings or other animals, have some inputs, right? So they can see, they can hear, they can touch, they can taste, etc. And they have some outputs. And we can think of these as modalities. And human beings, for example, have certain input modalities, certain output modalities, and they can perform a wide range of tasks as long as the tasks are supported by those modalities. And so what we are trying to do is design systems not based on what tasks they can do, but on what modalities they can support. So the NLP field has been quite successful in creating general purpose models. There's one very interesting thing about the NLP field. So the tasks and benchmarks are extremely diverse. They're very complex and highly non-trivial. But if you think about the structure of these tasks, they're quite homogeneous. Most of these tasks can be represented as sequences of words as inputs and sequences of words as outputs. And what that allows NLP researchers to do is to think about general purpose vision models as seek-to-seek architectures. And that's exactly what we've seen over the past few years. And as you start building architectures that can do everything, then you can start doing some very interesting things. You can build architectures that are completely task agnostic, that can learn from a few examples, And in fact, people have started showing that they can even learn to do tasks simply by describing the task, not even providing an example. Things are a lot more complex when you think of computer vision tasks. There's lots of different tasks, and each task seems to sort of have its own inputs and output structures. If you look at VQA, you have to provide a text input and a text output. If you look at depth estimation, you provide an image as an input and image as output. If you think about segmentation, you're providing images as input and text and masks and confidence scores. So clearly, tasks in vision are far more heterogeneous. And our goal in general purpose vision is to think about how can we take this sort of complex space and still build unified architectures. So tenet 2 of general purpose vision is that we'd like to build architectures that can perform tasks in skill concept combinations that have not been seen in training. So what do I mean by skills and concepts? An example for concept is a dog or a cat or a person, a sort of nouns or sort of entities that you see in images. An example of a skill is like VQA, the skill of question answering. And so here, what you're seeing on this slide is the skill of VQA being applied to the concept dog. Here's another example where the skill is localization, the skill of drawing bounding boxes around entities, and the concept is cat. Now imagine that you have training data for answering questions about dogs and training data about localizing cats. What you'd like a general purpose vision system to do is sort of factorize learning. Learn how to perform certain skills and learn how to recognize certain concepts. And now if you have unseen combinations, you'd still expect your models to do well. Interestingly, today's models do not do well in skill concept factorization. And there's a lot more work to be done. And the third tenet of general purpose vision is to design architectures that can learn new tasks. Of course, there's a whole field of continual learning that applies here. And these are the kinds of questions that are also very relevant to general purpose vision. How do you learn new tasks? Tenet 1 has already told us that we want to focus on architectures that can learn new tasks, but it's also important to design learning algorithms that can allow you to learn new tasks without forgetting old tasks. Okay, so now I'm going to talk about sort of 3 incarnations of general purpose vision systems that we have built over the last year or so. And I'm going to start with our first model, GPV1. So GPV1 was a model that could input an image, input a sort of a prompt, if you may. It can be a question, it can be something simple like describe this image, or it can be a prompt to localize a certain category. And it supports a few different outputs. It supports text output, it supports bounding boxes, it supports relevance scores, and it has no heads for specific data sets or benchmarks. So for example, if we can build a model for VQA and OKVQA and VCR, we don't have different heads for each data set. There's just a head for text, there's a head for bounding boxes, and a head for relevance scores. And the other contribution of this work is to think about how do we start measuring skill concept factorization. And for this, we designed a new split of the COCO dataset, where we can split the COCO's dataset into seen and unseen concepts and start thinking about the performance of models when they haven't seen, for example, localizing chairs or answering questions about cats. If they've never seen that combination, are GPV models still able to do this? So in this talk, I'm not going to focus on details of architectures, but I'm just going to tell you sort of at a very high level what this architecture brings to the table. So the interesting thing at the input is that the input is based on modality. So you have a language input where you can give the prompts for your tasks, and you have a visual input. And the outputs, sorry, this is a bit occluded, but the outputs,
okay, am I getting that? Okay, yeah. minimize this one so that
Like this?
yeah. Okay, I'll just yeah. Okay, and then just move it down,
Okay, great.
and then you can.
Fantastic. Thank you. Works. Great. And if you look at the outputs, we have a language decoder, and we have a method that allows us to draw bounding boxes and get relevant scores. And so now the language decoder can support multiple tasks like captioning, question answering, and the bounding box decoder can support tasks like localization, referring expression grounding, etc. And so the important thing takeaway here is there's no more task-specific branches, but what we call modality-specific branches. And if we take this model and test it on this new split of COCO, once again, I'm sort of keeping out certain low-level details, but happy to discuss them later. So this new split has a test set, but we measure performance on seen skill concepts and unseen skill concepts for 4 tasks. And so if you start looking at numbers here, the key takeaway here is that when you build general purpose vision models and when you train them to perform multiple tasks, you start seeing improvements on specialized models. But particularly, you start seeing improvements on unseen skill concept combinations. But of course, this also tells us that significant gaps still exist, and there's a lot of work, a lot of progress that is needed to build better, powerful general purpose vision models. So this was GPV1, where we thought of the architecture in terms of modalities. Then comes GPV2. GPV2 improved upon this architecture, but our key contribution here was to say, well, so far we've been learning about COCO, and COCO teaches us about 80 tasks. How do we scale these models to 10,000 concepts? I want to localize almost any species of flower or any species of an animal. How can I scale this without spending a lot of money? So here is the GPV2 architecture. I'm going to tell you a little bit about the architecture because it sort of is important in order to utilize web scale data. So as we thought about the architecture, every incarnation of general purpose vision model that we built kept thinking about, well, I can do 4 tasks with GPV1. How can I do 8 tasks? How can I do 12 tasks with the same model? And so now we have a third input modality, which is pointing, which allows the user to ask pointed questions, which allows the user to say, I would like you to generate a description of this particular region in the image, which of course starts getting into more interesting tasks in computer vision. So GPV2 supports more input modalities than GPV1. The other thing that we started doing was we started leveraging powerful language models, which provides some very nice gains over GPV1. And the third thing is we started thinking about our output modalities a bit different. So in the past, modalities for bounding boxes and modalities for text outputs had different parameters. But we started thinking, how can we get these modalities closer and closer? And so I'm going to skip over the details here, but it suffices to say that we use a text decoder for almost all tasks in GPV2, which starts allowing for even better skill concept transfer because the architecture turns out to be more homogeneous than GPV1. But the most interesting thing about this project is how we scale this. So let's think about how we use computer vision datasets today. The way we use them is, for example, COCO. COCO teaches us about 80 concepts, and it teaches us to perform many different skills. And COCO costs a tremendous amount of money. And this is just COCO detection, but there's, of course, VQA, which is based on COCO, and COCO captioning, and all sorts of datasets, each of which cost hundreds of thousands of dollars. So how do we go up to 10,000 concepts? So our key idea here is that we should be using computer vision hand annotated datasets not to learn concepts, but we should be using them to learn skills. If you want to have a particular skill, I'm going to give you a phrase and you need to localize all the nouns in this phrase, right? So some sort of a noun referring expression comprehension. This is a niche task and you need examples for this. So let's use computer vision data sets to learn skills. And let's use image search to learn concepts. Image search is extremely powerful. You can scale to tens of thousands of concepts, and you can learn about lots of niche concepts that it's just not scalable to get annotation data for. So for example, here, I'm showing you examples of hibiscus, a flower. But not only can you get images for hibiscus on image search, but you can also get, I want a red hibiscus, I want a white hibiscus, I want a ballet dancer who's jumping, who's performing, who's stretching. And so you can start getting examples from image search for nouns, verbs, adjectives, and all sorts of combinations. And what's very interesting that people don't realize is image search data. If you purchase image search data from search engines like Bing, they're actually quite inexpensive. So we obtained data for 50,000 concepts, which totaled about 1 million images. The quality is very high, and it cost us less than $200. And of course, computer vision data sets for a lot of tasks are already present. So really, if we look at annotation data in this new way, you can start scaling up models fairly inexpensively. So we collected this large data set, which we call Web 10K. It has over 10,000 concepts, and there's nouns, verbs, and adjectives. And then we converted web data into a sort of a QA format, which makes it very easy for us to query and train our models. And of course, web data is high quality, but isn't noise free. So the val and test sets were manually verified on Turk, and then we've cleaned this up, and these are released for everyone to use. So here are some examples of web data. So you can see that there's a lot of diversity in the nouns, but there's also a fair amount of diversity in the images themselves. And then if you take buffalo, for example, there's lots of verbs about buffaloes. Or if you take armchairs, there's lots of interesting visual attributes about armchairs. And if you think of this sort of tensor of nouns, verbs, and adjectives, web data allows you to get a more full tensor, which allows you to learn about concepts better. And these concepts vary greatly. If you look at visual embeddings, and if you use something like TSNE, you can start seeing that we have lots of different vehicles and clothing and animals and sports equipment and so on. Okay, so once we have web data, the way we trained our models was we started multitasking, not just on COCO data to learn skills, but also on web data to learn concepts. And we tried out 3 models: GPV1, which we had built, VLT5, which has come out of University of North Carolina, and GPV2. And for each of these models, we looked at what happens when you provide web data and what happens when you don't provide web data. And the key takeaway here, this is a big matrix of numbers, inappropriate for a slide for a talk, but the key takeaway here is, as you start adding web data, all models start improving because their understanding of visual concepts hugely improves. And especially on COCO, the improvements are very limited because COCO is only testing 80 concepts. But as you go to the tail in DCE, which is a new benchmark, and of course Web 10K, which is this manually annotated or manually cleaned up benchmark, you start seeing very, very large gains on the performance of these models on tail concepts. And then we find that GPV2 also provides very large gains and also outperforms other models. Interestingly, since we have now scaled to 10,000 concepts, models start showing some very interesting zero-shot performance. So here are 2 data sets. One is called situation recognition and one is called attribute recognition. And we haven't trained on the training data for these data sets. But we get pretty respectable zero-shot performance for GPV because you can take any task as long as it's within the supported modalities. You can query your model and see what it answers. So here's another interesting thing you can do since you can ask a GPV to do any task. You can start chaining GPVs. So human object interaction is a fairly sort of involved task. You have to find all the human beings, you have to find all the objects they're interacting with, you have to talk about what verbs, like is this person holding, is this person driving, etc. You can just invoke GPV2 as a function in your code. You can first ask GPV2 to locate people, then you can ask GPV2, well, now that you found a person, I can point at a person and say, what is this person doing? So sort of you can use prompt engineering to perform complex tasks with a general purpose model. When we look at GPV2's qualitative examples, we see that it far exceeds in terms of visual vocabulary than models that are not trained with web data. GPV2 can also transfer concepts across skills, which is what we were looking for. So for example, SUV or school bus or pickup truck, well, maybe school bus is in COCO, but SUV certainly isn't a localization category in COCO. But it has learned what SUVs look like through web data. And so now it can do other tasks, other skills on the concept of SUV. And the unique thing about web data, which static data sets in computer vision cannot give you, is they can be updated. So COCO was obviously created before the whole pandemic started, but web data keeps refreshing. And so we took a series of queries to do with COVID, whether it is COVID masks or vaccination cards. And then we queried Bing and took those images and fine-tuned our model. And now the model can start performing tasks on all of these concepts, which is quite interesting to see. Okay, so now I'm going to move to the last part of my talk, which has to do with what do we learn from GPV1 and GPV2, and what are the limitations, and how do we improve upon these? So one of the key limitations of GPV1, GPV2 is we've started thinking about models in terms of modalities. But the number of modalities is still limited. We're still thinking about text outputs. We're thinking about bounding boxes. We're thinking about some relevance scores or confidence scores, but we're unable to go to the next level. We're unable with these architectures to go to tasks like image generation or image inpainting or key point estimation. And so how do we get to this next level? And that's why it forced us to go back to the drawing board and sort of think about how do we build truly unified architectures? And then we came up with unified IO. So unified IO can input many, many different modalities or many sort of input types. You can input images, you can input language, which is what most models support. But now you can input masks, segmentations, bounding boxes. You can also produce an incredibly large type of modalities. So depth masks, segmentations, surface normals, these are typically tasks that are performed by highly specialized models. But unified IO allows you to produce pretty much any modality that you can think of when you think of single images, not videos. So the number of tasks that unified IO supports turns out to be very, very large. It can support tasks in classical vision. It can support, of course, vision and language tasks with GPV2 also supported. And it can also support NLP tasks. So let me briefly introduce how we're able to perform this very large set of tasks with a single unified model. So here's a quick overview of the architecture. So our goal with unified IO was to keep things simple. How do we build a very non-customized, simple architecture for so many tasks? So at the core of this architecture is something incredibly simple and well-known in NLP. It's a transformer encoder and a transformer decoder. This model, unified IO, accepts discrete input sequences. So sequences of tokens that have been drawn from some discrete vocabulary, finite vocabulary. It also produces discrete output sequences. So obviously we're in computer vision, so unified IO must be able to input an image. So here we take an image, we produce patch embeddings, and then these embeddings are provided as discrete input sequences. There is no CNN involved here. Now let's take the simplest task that most models can do today, VQA. So in VQA, you provide an image and you provide a question, the question is encoded using sentence piece encoding, and the decoder is also sent to a sentence piece decoder to produce an answer. So far, there's nothing particularly different from unified I/O and previous incarnations. Now, this is where it gets interesting. Let's say you have a task saying segment the car. Providing the task prompt is easy, it's just language. But the output now involves producing a binary mask. So here we take inspiration from vector quantized variational autoencoders. So I won't go into the details of what a VQVA is, but this is work, I mean, there's a whole subfield in computer vision that has built these kinds of models. And you can think of these models as sort of compressors and decompressors. So you can take an image, pass it through a VQVA encoder, and what it gives you after quantization is a discrete set of tokens. And these tokens can now be passed to the decoder to get back the original image. So they're like an autoencoder, except it goes through a quantization process. So what we do in unified I/O is when we say segment the cat, we do not train it to generate pixels. We train it to generate the set of sequences that correspond to that image that would have been produced by a VQVA. So now if we say segment the cat, what you really want to do is you want to produce 1, 3, 22, 10, 10, 80, these sort of 16 numbers here. And if you produce those numbers and you pass them through this VQVA decoder, you'll obtain this image. And so now you can see that a task that requires an image output can be thought of as a sequence to sequence task. Now you can do this for an arbitrary image output. This isn't rendering nicely on the projector, but this is a depth image for this task, for this cat in front of an umbrella. So if you say, what is the depth map of this image? Once again, you input it as a sequence and you predict the discrete tokens that would have generated this depth image. Now, if you go to structured outputs, whether it is key point estimation, whether it is bounding boxes, whether it is scene graphs, any sort of structured output, these structured outputs can be sort of transcribed into language. And so structured outputs can also now be thought of as a seek-to-seek task. And so what I'm showing you here is sort of our idea or our vision of thinking about this entire space of computer vision tasks as discrete sequence generation, which allows us to train a massive number of tasks in a joint manner with unified I/O, with a single model. Okay, so now that I've told you a little bit about the unified I/O architecture, it's probably starting to get clear that you can throw any number of vision or NLP tasks at this model and train it jointly. And what we've done is we've taken 80 data sets in vision, vision and language, and NLP, and done sort of massive multitasking, which is a huge engineering effort. And what we've really tried to do is avoid any sort of task-specific tweaks or tricks, because our goal is not to get that extra 3 points on one task. Our goal is to show that you can really perform lots of these tasks together. So we don't do things like siderow optimization or cut paste, augmentation, label smoothing, etc. We really train it in an extremely vanilla way. We have a way of sampling data from 80 different tasks. We use large batch sizes, and then we train 4 different size variants. So we have a small model that allowed us to sort of like experiment with this. And of course, we have a large Excel model, which is about 3 billion parameters, which is what obtains the best numbers. So in order to evaluate this, we used the recently proposed GRIT leaderboard. So GRIT stands for General Robust Image Task Benchmark. And the purpose of GRIT is to encourage researchers to produce models that can perform a diverse set of tasks. So you can see here that GRIT has things like categorization, localization, VQA, It also has things like surface normal estimation. And this is a fairly new leaderboard that came out about a month ago. So there's a few entries to the GRIT leaderboard already, and we have submitted GPV1 and GPV2. The key takeaway here is that you can see sort of clusters of models. Some models can produce vision and language results. Some models can do surface normal. Some models can do segmentation, key point, and detection, which is mask-R CNN. But what we see here is Unified IO can perform all of these tasks. What is also, there's a few interesting things in this slide. It can perform all of these tasks. It is not really designed, or we haven't put in the effort to hand tweak hyperparameters, also because we just couldn't afford that amount of compute. But compared to previous models, on 5 of 7 tasks, it's already providing state-of-the-art results. Another interesting thing is that Unified IO is providing strong improvements as you go from small to base to large to Excel. So for example, these are the 4 models in Unified IO. And if you look at these, all which stands for the average score, it goes from 45 to 65. And this implies that there's still a lot of sort of performance that we can extract out of the system by scaling it up. And that's not surprising because this system is trying to perform 80 different tasks. So you're going to need a lot of parameters in order to be able to perform these tasks. Okay, so with that, I'd like to end the talk with some takeaways. So we have been thinking about how do we move from specialized systems to general purpose vision. Models that have a general architecture that can factorize concepts across skills and sort of have a very general learning mechanism. GPV1 and GPV2 were task agnostic architectures that made very good progress towards this goal and taught us a lot about how we can think of tasks and modalities. And recently we've presented Unified IO, which is a GPV model that supports a very large number of diverse tasks. But of course, it's very clear to us that we're just scratching the surface with general purpose vision. There's lots and lots of interesting things that we can do in the future. Of course, there are obvious things like how do we support videos? How do we support audios? But there's also very interesting things like when we look at our model outputs, we still find that skill concept transfer is quite limited. Even though you have learned to do one skill on a concept, you don't always perform another skill on the same concept as effectively. So with that, I'd like to thank a long list of collaborators who worked on these projects. I'm happy to answer questions. Thank you.
Yeah, so I think you can come towards the mic and let everyone online.
We give the mic.
I'm curious about the applications of the multitask and multimodal capabilities on explainability. So let's say you ask the model, what is it? It says a cat. You talk about training the models. Where is the cat? So I'm wondering if there were any experiments on explainability or training with the latest model.
Thank you. That's a nice question. We haven't done any formal analysis on explainability, but we have demos of GPV1 and GPV2 up, and we'll have Unified IO up as well. And I like to play with these demos sort of in the way you've described it. So we see models that can, we see examples where the model can effectively answer a question, but sometimes it'll fail at a VQA question. And the first thing I end up doing is saying, well, maybe it didn't answer the question because it did not know what a rhinoceros is. And so I'll ask it, can you tell me where the rhinoceros is? Or can you tell me what is the color of the rhinoceros? And then if it can answer that question, then I would assume that it should be able to piece those pieces of information and answer a downstream question. This also can take the shape of the argument of consistency. So what we've seen is just because a model can answer X and Y correctly doesn't mean it can answer Z correctly, even though Z probably entails X and Y, because models aren't really optimized to be consistent. And so we're thinking about ways of getting these models to be consistent. I think if models start becoming more consistent, then you should be able to probe them for explainability. Today, if a model gives you a reason why it can do something, it doesn't really mean much because things are quite brittle in the background. But great question.
So one thing I didn't understand, like if you have a new task, like you have already pre-trained it on your whole set of tasks, and now you have a new task. How do you adapt to that task? You just this is one question. If you haven't had time for another, how do you check if you get some bias from one task that affects another task?
Yeah, so the first question was, how do you learn a new task? So learning a new task obviously requires new training data. But the way we're thinking about this is, we'd like people to be able to provide training data and not know anything about the architecture to train this model. And when I mean people, I'm not meaning people in this audience. Everyone is, of course, working in computer vision and wants to know the details. But an end user or an application developer should be able to train a new task just by giving training data. Sort of how application developers these days are starting to think about using GPT-3 for their work. And the second question was, does the bias of one task affect the other? Absolutely. So we've seen that models, and this is well known over the last few years, but we've particularly seen it in GPV systems, models latch onto biases. So for example, a simple thing like if you train it to predict captions from conceptual captions, you start getting very low scores on COCO captions if you do not fine tune on COCO, because COCO captions have been written by some set of annotators with some prompts and have some language biases. They use certain kinds of language, maybe they're from some part of the world. And so we have debiasing techniques which can mitigate some of this. So the way we do it is we look at the probabilities or the log likelihoods of tokens that you see during training, and we simply weigh them down so that it can encourage other concepts to surface up, even though they're not seen in training data. These are, I would say these are simple but effective techniques at debiasing, but I think that's a huge problem.
Thanks, that was really interesting. So clearly this kind of work falls in the bucket of works which is coming out recently, which is saying that if you take vision tasks and you model it as sequence to sequence, then you can leverage large scale data and have these really flexible models which can do really amazing things. One thing, so a specific question, but then a more general one. So one thing which always occurs to me is why should we assume that this autoregressive training method should scale to vision or is relevant to vision data when many of these tasks don't seem autoregressive in their nature? And then also more generally, where do you imagine this balance, finding this balance between domain specific engineering and being able to have models which can scale flexibly to this kind of setting?
So you're right. I mean, from a sort of the way I have been brought up in the computer vision community, it feels quite unnatural to think about images in an autoregressive way. I've been thinking about images all of my career as 2D maps of pixels. I mean, convolutions are quite new. When I started off, I was thinking about SIFT features and HOGs and sort of like but how do you take regions and how do you describe these? And then how do you combine them to form sort of embeddings of images? But I think even prior to Unified I/O, a lot of work in sort of vision transformers has shown us that I think machines are able to treat these as sequences. Because even though you treat them as sequences, there's a lot of positional embedding information that still tells you that, token number 23 was to the top and to the left of token number 35. So when you think about when you're modeling them, Unified I/O sounds like a sequence, but really it's sort of a nonlinear transformation of this 2D space. It sort of looks like a sequence, but still probably retains a lot of the spatial information. So I don't think of it as a disadvantage to be autoregressive because a machine is modeling it. If I had to do anything with an image, I don't think I would be able to think of it in an autoregressive manner. There is one disadvantage to being autoregressive. An autoregressive decoder is tremendously slower than a CNN decoder, where things can happen massively in parallel. That is one disadvantage of autoregression. And what was your second question?
More generally, so the benefit of autoregression is that it's very flexible framework, and you can throw all the data at it and just have one model. But for all these problems with implementation, you can imagine it more efficient with encoding a prior the architecture. And how do you imagine us moving forward, finding a balance between these specific general large scale?
So one of my collaborators, Derek Holm, was talking about this yesterday, and I can quote verbatim, not literally, but loosely based on what he said yesterday. So he was talking about how many years ago, many decades ago, we had very specialized computers, and they were built to do certain things. And when I mean computers, I don't mean this crazy powerful laptop. I mean this big room of things that was used to add a few numbers or something like that. But as we got to more sort of general purpose computing, we didn't think of these computers as less capable than specialized versions. We thought of how do we build applications and think of the computing machinery as just some basic structure to build on. If we move to more general purpose architectures, it's possible that people think less and less about how do we use the right CNN or how do we use this particular component to speed this up, but instead think of slightly more higher level abstraction. How do we do, people are thinking NLP, people are thinking about how do we do prompt engineering? How do we provide the right inputs so that you can get outputs? How do you do few shot learning? Because the low-level architecture is starting to become generic. I'm not suggesting that what we have today is good enough to be your general computer, but I think this is a sort of, philosophically, this might be an interesting way for computer vision to go. Sure.
Yeah. And
hey,
this is a great talk.
Thanks.
Is this all right?
Yeah, this is fine. I'll repeat the question.
Okay. So I was kind of wondering, a lot of these other sort of like large scale multitask things are taking advantage of language to language tasks, but yours fundamentally doesn't do that. You think the text to text would help your model, or you think it's somewhat tangential to the vision tasks within this model?
So we are doing text to text. Is your question, are we not doing text to text?
Okay, I guess that's that.
Yeah, so
you're training with autoregressive language.
Yes, so we are also jointly training on, for example, squad question answer, or paraphrasing, or MNLI. And also our pre-training has very large text corpora with masked text modeling. So we find that, and of course, our architecture, I didn't go into the details, starts off from a T5 model. So it's heavily based on NLP architectures, NLP tasks, and NLP pre-training. And we do find that, that's helpful. So I guess, yes, we are doing what you suggested.
If you want to answer more questions.
Sure, I'm happy.
If there are any, yeah, please.
So I was wondering whether since you're training a unified model for so many different tasks and modal uses input, did you find it hard to optimize such a model that certain tasks sort of go over the optimization procedure or certain modalities like become much more dominant?
So the person to answer that question, as you were asking the question, he just got up and walked out, but he was the sort of the, I guess, the one of the two main creators of this task, of this model. So yes, it was actually very non-trivial to optimize unified IO. And well, I guess there's two reasons. One is, in the past, we have worked with 4 data sets, smaller models that fit on like 4 GPUs. And here we were using Google's TPU cloud and 80 tasks. And it's sort of it's a bit of a science and a bit of an art to do gradient descent with such large models. And this was a very sort of learning experience for us. There's a lot of gradient explosion. There's a lot of like NANs that happen. And you have to sort of keep babysitting your model, almost like what we used to do with smaller models 5 years ago. But I don't think we really understand how to train these large models. And so it is non-trivial. But I guess your question is talking about how do we sample these tasks? So there are some benchmarks that unified IO does very poorly on. And when we started digging into this, we realized it was just because the training data for those benchmarks is masked out by these much larger data sets. Like Cocoa-based data sets have a lot of data. If you go to a niche data set, you probably have like 2,000 questions or 4,000 captions. And so we do have some sort of temperature scaling in order to sample things a little bit more uniformly, but smaller tasks do get overshadowed. But we have not done any task-specific fine-tuning. But I would expect that if you took this model, in just a few hours of fine-tuning, you should be able to get those small tasks up, because a lot of the things that have gone away are just biases. This word doesn't exist in the vocabulary in aggregate, so I'm just going to reduce the log likelihood of generating this word. Those things can get boosted up fairly easily. Thanks.
Yeah. Okay. Thanks a lot, Aniruddha. This was a great talk. And so we're going to have spotlight talks after this. So stay tuned. Thanks. Thank you so much. Hi. I see. Okay. Yeah, I think we. Okay, so we have 2 speakers are joining virtually, 2 talks. So if you could share your screen, that would be great. Thank you. Can you share the screen, QA Young?
Yeah.
Okay.
My screen.
Thank you.
Okay.
Which one?
Move this window there. The one with this shared screen.
This? No. Coming back.
Can people online see the slides?
He doesn't share.
Yeah.
Yeah.
But we don't see the slides.
Yang, can you share your screen?
I think I'm the 4th talk. So should I share now?
Yes.
Okay, great. Yeah, we can start.
Okay, I will start.
Can you start?
Okay, cool. Okay, hi everyone. I'm Yue.
No, we don't hear anything.
Can you hear me?
I can hear you.
Try this. Okay. Can you?
Hello.
Can
you hear me?
Yes, this is good. Thank you.
Okay, got it. Thank you. So, hi everyone. I'm Yue from UPenn, and I will present our work, Induce, Edit, Retrieve, Language-Grounded Multimodal Schemata for Instructional Video Retrieval. So this is a joint work with Jungwon Kim, Animus Panagopoulos, Mark Yaxka, and Chris Kellenberg. So what is a schema? Schema is a set of rules or instructions or recipes like people use to perform daily tasks. And an interesting thing for schema is it can be generalized. So when people are encountering some new tasks, they tend to use their previous knowledge and adjust it for the new task. So for example, a person knows how to bake cake. Apparently, he can use the knowledge of bake cake for the big cupcake, big cheesecake, or even for bake cookies or bake fish. At least some knowledge about how to use the oven can be used for bake fish. So how can we design a system to mimic this process? So here we introduce our IER system, which includes 3 stages.
For the first stage is induce. So the input is a task and a set of videos about this task. And we can output a set of natural sentences as a schema. So for the second stage is edit. Given an unseen task and there's no videos for us to learn the schema, you can use language models to modify or edit the existing schemas and adjust it for the new task. And the third stage is retrieve. It's the application of schema. We can use schema to help us improve the long video retrieval performance. So for the first stage, schema induction, so we have a task, for example, big chicken and a set of videos from YouTube. We can align the video segments with the WikiHow steps. So WikiHow is a how-to website, connects a lot of articles, teach people how to do daily tasks. So we collect 1 million of WikiHow steps and align them with the video segments. And we count the frequency of each step occurs in this task. And then we pick the top frequent steps as our schema. Here's an example schema of big chicken. So we use the how to 100 million videos as our data, and we learned over 20,000 schema in our schema library. So for the second stage, schema editing, given an unseen task and there's no videos for us to learn the schema, we can retrieve a similar task in our schema library and edit it to adjust it for the new unseen task. For example, for big chicken, we use textual similarity and image similarity to retrieve a task. Like for big fish, we can retrieve a task big chicken in our library. And then we design several editing modules to edit the existing schema for this new unseen task. So the first one is quite straightforward. It's called object replacement. If we want to use the steps of big chicken for big fish, we can simply replace all the chicken tokens in the steps with fish. Here are some other examples, like use cook ham steps for cook lamb. We just replace ham with lamb. And the second module is called step deletion. We found some steps are no longer suitable for the new task. For example, like inserting a roasting thermometer into the side of big chicken task is no longer useful for the big fish. We will delete it. And then we use sentence bird to compute a score between the task and the steps. And if the score is too low, we will delete that step. Here are some examples, like for transplant a young tree, there's a step, fill your pot with fertilizer. It's no longer useful for remove a tree. So we will delete this step. So for the third module, it's called token replacement. We use mask language models to replace some tokens with low probability. So for example, season the drumstick. This drumstick has low probability for the new task big fish. We will mask this token and then predict a new token from the vocabulary. Here we predict a new token fish, which is more suitable for the new task big fish. Here are some other examples, like for prepare fish, there's a step called cut the fins from the fish using kitchen shears. We will replace fins with shears and kitchen shears with steel scissors for our new task, prepare crabs. So the third stage of our system is how to use the schema for video retrieval. Our task is given a short query, which is a task name. We need to retrieve a long video. The video can be multi-minutes long, and it connects a lot of steps in the videos. So previously, we can just use the task name to do global matching, but the problem is we cannot have good alignment with big fish with all the video segments. But then with the help of schema, we can have better local alignment because we have fine-grained steps of the schema. We can have better local alignment with the long video and thus improve the retrieval performance. And we evaluate our system on the 3 data sets. How to Gen is a new split from how to 100 million. We split based on the tasks. We have 500 tasks for training, 5 for validation, and the rest for the testing. And we also evaluate 2 popular instructional video dataset, Coin and Youtube. And we compare with some baseline models, different ways to induce the schema. We have generation models
T5, GPT-2, and GPT-3. We also have a step inference model called GOSC. And we also got the Oracle schema written by human, which considered as the upper bound. So here are the results. As we can see, like almost all the models with the schema is better than the model without schema, which means schema guided video retrieval is a promising way to improve the long video retrieval. And our IER system is better than other schema induction method and getting very close to the Oracle schema. And we also show like with the schema, we can help more on the long videos. As you can see on this graph, with the increasing of video length, with the schema, the model with the schema has more improvement over the model without schema. And also we did some evaluation on the editing modules. We found when the task similarity is low, the editing is more important. So when the task similarity is low, with editing can help more on the compared to the model without editing. And we also evaluate on each editing modules by deactivate them one by one. And we showed by deactivating each of them will damage the performance, which shows our editing modules are all very beneficial. And another useful advantage of schema is it can be transferred because schema are in the natural language form. They are strings, so it can be readily transferred to other vision text model. So we use CLIP as our vision text model and plus the schema induced by the MIL in CE. It shows like by adding the schema, we can improve the performance of CLIP. So here are the summary. We propose our IER system which can induce schema from videos and edit schema for unseen tasks. And it can help retrieve on unseen tasks. And in the future, we plan to investigate the structure of our schema because currently our schema is just a bag of steps. So we can consider the temporal order of schema. Yeah, that's all my presentation. Thank you.
Thank you, Yue. I think for the sake of time, we can move to the next presentation, and we can take questions offline.
So shall I share my screen?
Yeah.
Yeah. Okay.
Yeah, sorry about the delays because of technical issues.
Can you see my screen and hear me well?
Yes, we can see your screen. Yeah.
Okay, so hello, my name is Guillaume, and I will present the paper Embedding Arithmetic of Multi-Modal Queries for Image Retrieval, which is a joint work with Mathieu Corde from Sorbonne Université and Matthijs Does and Olga Schwenk from Meta AI. So the task that we are tackling is text-driven image transformation. So given an input image, here a cat sitting on the grass, on the text transformation query, like change the cat into a dog, the aim is to retrieve an image in a database which corresponds to the input image transformed by the text query. So we want a dog, not a cat, which is sitting on the grass, and ideally we would also like to have the same color for the animal, but it's not always possible with the Retrieval database. So this is the task, and we contribute a data set and metrics to evaluate algorithms on these tasks. Also, we start from sorry, I have a bug in my computer. Okay. Yeah. Okay. So just to take here, we contribute. We propose a simple zero-shot method. And where we use it to assess geometric properties of multimodal embedding spaces. So our motivation is based on the observation that there are some geometric properties in word embedding spaces, like the embedding difference of a woman minus man and queen minus king or aunt minus uncle are aligned in a word embedding space, despite them not being trained for this specific property. And we have observed that it's also roughly the case for sentence embedding spaces. So we can compute the delta vector between cat and dog and add it to the vector a cat is sitting on the grass, and we get roughly the sentence a dog is sitting on the grass. So we wanted to check if it was still the case with multimodal embedding spaces. So here is the overview of the simple method that we are studying. Given an input query image and an input text transformation, we encode the three elements in a common multimodal embedding space. So typically we use clip. We compute the delta vector as the difference in text embeddings, and we add it to the image encoder. And finally, we perform a retrieval in an image database to retrieve the transformed image. We also parameterize the method by a scaling factor, lambda, which can help to enforce the transformation. Now evaluation, how do we evaluate algorithms on this task? We need to first check if the transformation was successful, and we need to check if the context has not been changed. So we tackle this by leveraging annotations from the visual genome dataset, subject, relation, object, triplets. So here, cat sitting on grass, and we propose to change either the subject, like cat to dog, or the action or relationship sitting on, or the object, here it's grass. And also we ensure that each transformation query has a valid solution in the dataset. So here is the overview with evaluation. So we take the caption corresponding to the image query, a cat is sitting on the grass. We just replace in the text cat by dog to get the reference caption, a dog is sitting on the grass. And then we will use this reference caption to score the output image with an image text similarity module. So it just assesses whether this image corresponds to that text. So in the end, we have a simple accuracy score. And we use Oscar as the image text similarity model here. So here are a few simple examples where we can change the subject, woman to man, the relationship, leaning on to jumping over, or the object, toilet to suitcase. And here we show an interesting example where it's a failure. We are not able to change kite into rail, but the bench has kind of a rail structure. Okay, so what do we do with our evaluation? So first we evaluate zero-shot clip embeddings. So here is a plot showing the accuracy score, transformation accuracy score, with respect to the scaling factor lambda. So in black we have the zero-shot performance, and we would expect 1 to be the best value, but we have actually observed that 3 is better in terms of zero-shot accuracy. And then we have tried to fine-tune the clip embeddings with different temperatures, with an image text matching loss on MS-COCO, and the different curves correspond to the different temperatures. And basically we show that higher temperatures lead to better transformation scores, and the best temperature is 0.1, which corresponds to a scaling factor of exactly 1. So yeah, the message is that vanilla clip embeddings are not very well suited for delta vector-based transformation, but it helps to fine-tune them with a higher temperature. And then another message is that we have tried to leverage the geometric properties of pre-trained text encoders like fast text, labs, and laser, which are sentence encoders. And the result is that it's not really useful to do that. But an interesting observation is that the best fine-tuning temperature does not depend on the text encoder. Thank you for your attention.
Okay, thank you for the to all the authors of the Spotlight talks, and that concludes our workshop. So this was the first time that we've hosted this workshop, and we hope that we can continue discussions in this area and talk about retrieval and multimodal open domain retrieval. All right, thanks everyone online for joining. Thanks everyone in person for a great experience for everyone, hopefully, and we'll keep in touch later. Okay, thanks.
Thank you.
Okay, bye everyone.